framework, which is, for the most part, self-consistent. But again, this falls into the category of interpretations of quantum mechanics, in that it does not make any predictions, at least as of yet, that can be differentiated from the more traditional interpretation of quantum physics. So we have no idea whether this has any basis of reality. So, if you have Schrodinger's cat who's in the box, are there parallel universes where he's doing all these things in the box at once? Well, it makes for a cute cartoon, but we have no proof of it. So then, okay, where did this whole holographic multiverse thing come out of? Well, this actually came out of string theory, which some of you may have heard of. It's basically an attempt to unify quantum physics with general relativity on a fundamental level. And there's this holographic principle in it, which basically proposes that all of the information representing the universe is represented or encoded on a distant bounding surface that's sort of at the edge of the universe. And the reason this is holographic is because it means that if you look at that bounding edge, which has one dimension of space-time less than what we live in, everything comes out of that gives us the appearance of our space-time. And so if there really is, a many worlds style universal wave function, then this distant bounding surface contains all of the information for all of the branches of the universe. And so if you could view this distant bounding surface, changing what part of it you view would sort of correspond to changing which branch of the universal wave function you're looking at. And so this then got misinterpreted by the quantum jumping people to say, well, if you shift your slice of the holographic multiverse, you can somehow jump from one branch to another. So what I want to emphasize is there's just so much wrong with this whole quantum jumping thing. Even if many worlds does turn out to be true, okay, there is no mechanism in it to intentionally shift between realities, nor retain memory of past realities. So, for example, the quantum jumping people will say that, for example, if you get lost or if you misplaced an object, because you're actually remembering where that object was or where you were supposed to go in the other quantum universe, and since then you accidentally jump to a slightly different quantum universe where the thing is in a different place, and that's not your fault. So there's no mechanism for retaining memory of the old reality while jumping to a new one. And then adding the whole holographic layer doesn't help at all. It just obfuscates it in more confusing stuff. So then they also claim things like remarkable healing or recovery or feats of athletic prowess or what we might think of as miracles are simply very unlikely branches of the quantum wave function getting jumped to. So where people have intentionally jumped to a very unlikely possibility where they can run the 1 minute mile or the American curling team can win the gold medal. Sorry, I'm Canadian, so I think the Canadian curling team should always win. So the problem here is, people are macroscopic systems, very wet and complicated and noisy, and all those things that I said can't be in superposition. Really, totally incapable of quantum behavior where we can, transform ourselves into a pure energy state and put ourselves in superposition and suddenly show up in some other quantum state. And pretty much everywhere where they say that quantum entanglement allows you to do things like transmit information backwards through time or to your previous self or to another incarnation of yourself in another branch of the wave function. No, that's not how entanglement works. Okay, and so they are doing pretty much everything wrong when they say that quantum physics does not mean that you can just throw out the rule book and throw out all the laws of physics and anything is possible, and even if it's very highly improbable, well, anything can still happen. No. All right, so now that everyone has stayed to the end of the talk, you are all winners of the uncertainty principle game, which means you are all entitled to a quantum of dishwashing detergent. But more importantly, you are all invited to ask me anything you ever wanted to know about quantum physics. Thank you.
All right, questions? Just raise your hand. I'll try to do my best to get you guys.
Okay, thanks very much. That was a great talk. I have a very specific question which I'd like to ask, and the reason I want to ask it is it's something that's very hard to Google. So, and it really needs to be asked to somebody who works in it, so this is my opportunity, I think. This being the atheist community of San Jose, some of us deal with the other half of the world, the theists, and one of the arguments is the cosmological argument for the existence of God. And this argument depends upon everything having a cause. So the underlying idea is that everything must have a cause, and so therefore we go back to the Big Bang, and you'll find these people really like the Big Bang because there was no, you must have a cause, and that proves God. So one of the quantum phenomena we have is spontaneous emission of radiation, and that's, if I understand it correctly, spontaneous. And by spontaneous, we mean not caused by anything. The other thing is pair production, where you have pairs of virtual particles that exist for a certain amount of time, and that brings around Hawking radiation if one of them gets captured by a black hole, blah, 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 blah. So can you answer the question, those phenomena that I just mentioned there, can we say with honesty that nothing caused them in the sense that we normally mean about causality?
Okay, so first of all, I think there's a difference between the way cause or causality gets used in popular culture and the way that it gets used in physics. So in physics, when we say causality, what we're usually referring to is if you have an event that takes place in some region of space-time, you can then form what's known as a light cone around that event. Basically, nothing can travel faster than the speed of light, and so you say, okay, if you have light, traveling from that event, right? How far can it propagate? And so you have this space-time cone around the event of everything that it could possibly affect by communicating with it through, say, light signals elsewhere in space-time. And similarly, you have a backwards cone of anything that could have affected it. And then you can build, nets of causality between different regions of space-time. And so when we say that two things are in causal contact, we mean that they are in each other's light cones. And when we say they're out of causal contact, we mean that they are out of each other's light cones. And so, okay, so first of all, when you say everything has to have a cause, right, if you translate that into physics speak, you're saying, okay, everything has a backwards light cone, right, in which there is some region of space-time. When you go back to the Big Bang, okay, that completely fails because space-time started at the Big Bang, so to speak. There was no before the Big Bang. There is no light cone before the Big Bang. So to say, so you can't really talk about it that way. When something happens like pair production or spontaneous emission, right, that event is still in the light cone of other events. So there are other things that are causally linked to it. What I think you mean colloquially, right, is there something else that happened somewhere in space-time that, if that had not happened, then the emission wouldn't have occurred or the pair production wouldn't have occurred. And so then what you're really asking there is, okay, was its wave function collapsed by something else, right? So, this thing is in a superposition of states. If we observe it having emitted a photon, okay, the fact that we've observed it having emitted the photon means we collapse its wave function, right? So it wasn't a superposition. Then we observed it. Now it's at a lower energy level, and its photon is over there. Okay? If nothing had observed it, it would still be in the superposition. Virtual particles pop in and out of the quantum foam while the system is in superposition, essentially. So they pop out and they pop back in before anything observes it. Okay? And so there, the entire process, okay, of emission and absorption happens while nothing has observed it. So then by definition, nothing has interfered with its wave function. Nothing has collapsed its wave function. Exactly. So in that way, you could say that what happens with virtual particles has no cause. However, that event is still in the is still in the light cones, right? So it is still linked in causal contact with other events. Does that kind of make sense?
It does. Thanks.
Okay. Something else that I do want to point out about the Big Bang, though, before going further, is there are a lot of theories, especially in quantum cosmology, where the Big Bang was actually a bounce. Okay, this is known as cyclic cosmology. So it wasn't that there was, a singularity that went bang. It's actually that there was a universe extended like ours that collapsed into itself, and then when it hit a very, very small quantum scale, like near the Planck scale, okay, then quantum gravity effects cause it to bounce outward again and start expanding. And so then that's a little different because, okay, there is still causal contact between things that happened, between things that happened in the contracting phase and things that happened again in the expanding phase. So then things that happened, so in this case there was a before the Big Bang, okay, things that happened in the previous universe, okay, can be in causal contact with things happening in the current universe. So that's a whole other sort of Big Bang issue, yeah. And then there's also this sort of idea of eternal inflation and multiverses, where there's actually this multiverse and then little pockets of space-time randomly go into inflation. So this means that a quantum fluctuation causes some sort of a potential field, maybe a scalar field like a Higgs boson or something, what we generically call an inflaton field. Okay, it falls off its potential, starts rolling down this hill, and it causes space-time to literally inflate or expand at an exponential rate. And so this is sort of like bubbles nucleating out of a bath. And then our universe is just one bubble. And then, okay, well, if we wind the clock backwards, right, our bubble collapses back into the sort of quantum sea, and then maybe are you in causal contact with other parts of the sea and, other bubbles that nucleate. We are then actually completely out of contact with other bubbles because you can't travel faster than the speed of light to beat that. But anyway, so yeah, it's more complicated depending on how you define the Big Bang and what was it that really happened there.
Well, that's all well and good, but you have to remember that God is timeless, spaceless, immaterial, and made of magic. So all of this is really just a waste of time. No, I'm just kidding. Easy question for you. Are we living in a simulation? And if so, do you have access to the cheat codes?
Oh, okay, yeah, we have some Elon Musk fans here. Okay, are we living in a simulation? Okay, and then that leads to the other interesting question: is it a quantum simulation or a classical simulation? Okay, so there's this whole field of information theory, and one of the things that it tries to do is it has all these concepts of, for example, information entropy to basically define, okay, how much information is present in the universe, how is that information changing? And so when you look at the observable universe, there's so many subatomic particles in it, the amount of information that is, contained in those particles and those interactions, you cannot store all of that in any sort of a classical computer system. So you can't have a classical simulation that can simulate the entire universe. You would need a quantum simulator, okay, to simulate a quantum universe. Now that being said, places like D-Wave are, building quantum simulators. So could there be some really advanced civilization that has a quantum simulator that is powerful enough to create our universe? And then part of that goes back to, okay, how big is the universe that they're living in? Okay, do they have access to enough energy and matter? And are there enough, subatomic particles in their universe such that if you link them all together and store information on all of them, you have enough capacity to model our universe? The answer to that is that it is possible, yes, and especially in a multiverse, it's very possible because there's infinite universes out there, and so if you have an infinite number of anything, then basically anything that can happen will happen at least once somewhere in the infinity. And so then if there's an infinite number of universes out there, one of them at least will contain an intelligent civilization that has a quantum simulator, and it's big enough to power our universe. So in that way, it's kind of impossible to rule out. Then there's a question of what's the likelihood that we're living in a quantum simulation. And so then this leads into all kinds of incredibly obscure probability arguments, and this depends on things like, are you a Bayesian or are you a frequentist, and how you classify probability across, branching wave functions and all that sort of thing. And people have tried to work out, okay, what is the probability that we are in so-called level 0, meaning not simulated, versus that we're in a simulation, level 1, or that we are in a simulation created by a simulated species, which is level 2, right? And then you can go all the way down the line to infinite levels, sort of like Russian dolls nesting in each other, or as one of my colleagues says, it's turtles all the way down. Get that reference, right? And, okay, I would say that there's no satisfactory way yet of quantifying that probability. People have come up with some schemes. I don't like any of them. They're not really mathematically rigorous. Some of them are even mathematically inconsistent. Someone may at some point come up with one that I find, rigorous and self-consistent and convincing enough. And then if they can, quantify for me what is the probability that we're living in a simulation as opposed to not, then I might sort of take that seriously. In the meantime, I really think that that's in the realm of philosophy, not physics, because you're not able to propose an experiment whereby you could prove it or disprove it. And it's sort of like the question of, are there intelligent species in other bubbles of the multiverse? Well, you can propose that there are or there aren't, but if we're not in causal contact with them in any way, there's no way that anything we can do can affect them, and vice versa, then that's, again, not a question of physics. It's a question of philosophy. Now the question you have to ask yourself, if you're really a skeptic, am I saying all of this to try and convince you this because I actually have the codes to the matrix and I'm one of the people controlling you all, and I'm trying to convince you not to overthrow my alien overlords? That one you will have to decide for yourself.
Okay, you're making my brain hurt.
Good, that was my goal, to eliminate the lesser brains in the matrix who can't accommodate this information.
Well,
see, I have to select the ones who can comprehend, and then you can come join the Illuminati with me.
okay, so...
And if you pay me enough money, I'm selling memberships to the Illuminati, by the way.
I'm not a physicist. Keith, your first question, he's a physicist, so he could get in the weeds with you a little bit. I'm a biology person.
Okay, so I did have a biologist in the audience.
So I appreciate you talking about the consciousness issue. I've certainly read about the microtubules thing, which just makes me mad. And so I'm glad you, of course, couldn't get into the details since you had a lot to cover, but certainly what I see is people taking the opportunity to elaborate on this consciousness concept to say that the universe has consciousness, which makes the whole thing ridiculous. It just it's meaningless that that's the case. But what I really want to ask you is to back up a little bit, just to in the lecture here, about the quantum aspect to biology. So you talked about quantum in biology having to do with electron level changes due to photon excitation, if I got that correctly.
Yes.
But really, it means that everything in biology is quantum, because ADP to ATP and back and forth, I mean, electron excitation is intrinsic to that whole process. And that is about as basic to biology as every life form, or pretty much as far as I know, is based on that, which means everything about biology is quantum.
So now we're getting a little bit back into the old debate of, okay, physics is really just applied math, and chemistry is really just applied physics, and biology is really just applied chemistry, so all biology is sort of applied physics to some level. So it is absolutely true that chemical reactions like adenosine triphosphate going to adenosine diphosphate are fundamental to all life. I guess what I sort of tried to highlight here is so there was this whole sort of classical chemistry that was understood before quantum physics was well understood, and there were these rules of classical chemistry that described how things interact. And could you model a biological process with basically classical chemistry rather than having to invoke quantum chemistry? The thing about photons getting absorbed and emitted and on the energy levels, this whole sort of photoelectric effect or reverse photoelectric effect, which is what Einstein highlighted, which is what actually led to the whole development of quantum physics. It cannot be explained using classical chemistry. And so if you ask why are plants green, for example, in that photosynthesis process, the energy levels of the electrons in various different chromatic pigments are arranged such that they, of course, only absorb photons at certain frequencies, right, that correspond to differences in energy levels. And those frequencies, it's hardly ever any corresponding to green light. So basically, they don't absorb any green light, and that's why we see it. In classical chemistry, there's no way to explain, okay, how is it that the green photons aren't absorbed and the other colors are absorbed? Because, you know, if you have some sort of continuous electromagnetic field, it's just exposed to energy, right? Plants can grab as much of that energy as they want and sort of spit out the rest, and the differentiation between different colored photons and different energy levels in the chromopigments doesn't come in. And so then you can't explain why plants are green. You can't explain why photosynthesis uses photons of certain colors at certain energy levels. Similarly, you can't explain details of the electron transport chain, because if you model electrons as classical objects, you know, they shouldn't be able to quantum tunnel, you know, the details of their traveling along the cell membrane. It doesn't work, okay? Whereas, you know, most of the chemical reactions that sort of happen about, you know, two ions come together and make something, or, you know, you have these complex biological molecules that are formed with, you know, carbon sticking to each other and that kind of thing. You could explain that all with classical chemistry without really invoking the difference between classical rules and quantum rules. So that's why I highlighted what I did. You're absolutely right that in a way all biology is applied physics, and part of that is why I try to tell biologists I'm superior to them, because, you know, I can subsume their entire paradigm under mine.
All right, sorry guys, it's getting a little late. I know we have a lot more questions, but we got to start wrapping up. So we're going to start wrapping up. Everyone give their round of applause to Miriam. Miriam, from what I understand, she's going to stick around for a while, so if you do have any other questions, feel free to go up and ask her. If you can help break down, that'd be great. We have a lot of equipment that we need to break down. Otherwise, please stay, hang out. A lot of the boards are going to hang out probably at least till 9:30 anyway. So everyone have a great night. If you can stay, please stay. We encourage it. If you can help, we encourage that even more. Otherwise, have a great evening. Thanks for coming.